materials, there is also now a link there to a zip file with a copy of all of the lecture notes as well. So that's an easier way to get the lecture notes without having to deal with Microsoft's security nonsense. Okay, so hopefully if you have a look at the Practical Web VIMC website for the course, you'll be able to get a copy of all the lecture notes without any problems. If you're still having trouble, just let me know and we'll sort it out at the break or the practical session. But now we're going to dive straight into starting to build our own dynamic population models with Katie.
Thank you. Good morning, everyone. Hope you're well rested and ready for day 2. So yes, we're going to start using some of the things that we saw yesterday in terms of differentiation and integration to look at some differential equations and then look at some models for things. So this lecture, we're going to go through what is a differential equation, what do they look like. Hopefully by the end of it, when you see one, you will be sort of familiar with what the different components of it are and how you might start using it or trying to understand it. We'll go through some examples of what they can be used for. Obviously, we'll be using them for epidemiological models later on. And then we're going to talk a bit about the process that you use when you're developing a model. So what are you thinking about? What are you trying to aim for? Then once you've got your model, we'll talk about how you might examine it, how you might explore its behavior. And that's including solving it, but also thinking about other ways we can get information on what it looks like. And then we'll come on to just a small bit on how computers solve differential equations. So, what are they? Well, usually when we're talking about a differential equation, we're thinking about a rate of change of an unknown or dependent variable as a function of a known or independent variable itself and some model parameters. And those model parameters can be changing, they can be constants. We can look at that later on. So starting with an example, and we've seen something a bit like this previously. So here we've got our dn by dt. So here you might be thinking about a population n, number of individuals, and you might be thinking about how it changes with respect to time. So this equation is giving us some idea that the change of n with respect to time is negative, is decreasing by 5. So we're going to be talking pretty much exclusively about ordinary differential equations. So this is where the derivative of things like n only depends on t. We're not necessarily, except for one example, I think tomorrow, will we be looking at where the derivative depends on multiple things. We're just mainly focusing on where n is a function of t. So differential equations can take lots of different forms. We'll be seeing this one a lot, where we've got dn by dt is equal to minus lambda. Here, lambda is just a constant, just the parameter in our model, and then we've got n on the right-hand side. So the rate of change of n with respect to time depends on the population and this parameter, lambda. But they can take lots of different forms. So here we've got a second-order differential equation. So we've got our first derivative and then our second derivative. And over here we've got something involving a trigonometric function. Again, we'll be seeing this one a lot. These ones, not so much. Okay. So, as I said, we'll mostly be focusing on ordinary differential equations. So what do they look like in general? So here we've got our derivative of n with respect to t, and that is some function, so f is just a function here, of itself, n, the independent variable t, and then some model parameters. So these could be alpha, b, gamma, they could be any other constants you might be interested in. And we're always, in this format, thinking that n is a function of t. only. That's what we're interested in. How is it changing with respect to time? So, we know how to recognize them, but what they're useful for. So, we use them a lot in modeling because we want to describe some relationship, some change of our dependent variable given a change in our independent variable. So again, it's much easier to think of this in terms of examples. So here, we've got our differential equation. We've got our derivative of n with respect to t. It depends on itself. And here, n is a number of particles, lambda is a rate of decay, and t is time. So this differential equation captures the change in the number of particles with respect to time, and we're talking about radioactive decay in this format. So we'll come back to the modelling process a bit later on, but essentially what we want to capture here is how is this changing? We formulate our differential equation, and then we can either solve it or explore its dynamics to get some insight into the system that we're interested in. There might be other things going on, but we've thought about the particular bits of the system that we're very interested in and designed the equation around that. Okay. What does it look like if we solve this differential equation, which we will in a moment? Well, we get a decay in the number of particles. So initially, this decay is quite fast because the rate of change of n with respect to t depends on the population of particles. So if we start with a high number, if n is large, then this rate of decay is also large. So we've got a steep rate of decay at the beginning. As time goes on, our population of particles, n, gets smaller. And because the rate of change of n with respect to t depends on the population size, this rate gets smaller as well. So we start with a steep gradient, and then it levels out. So we've got exponential decay in this format. Okay. So hopefully, through the course of this, course, but hopefully today, you can see some of the reasons why we might be interested in differential equations and them being helpful for when we want to explore different dynamics. I've got a couple of examples. So you've seen something for radioactive decay. Can you still hear me? Yes. Great. Okay, you've seen something for radioactive decay. We might also be thinking about movement of something, so an apple falling due to gravity. So here we've got x as the position of the apple in space. And we're thinking again, how does that change with respect to time? So if we differentiate the position of the apple once, we get the speed that it's moving with respect to time. If we differentiate it again, so differentiating that position with respect to time twice, we get the acceleration. So we can write an equation for the acceleration of the apple due to gravity. There's other stuff going on. We know that the apple is going to be affected by wind resistance, all of these other things, but maybe we're only interested in exploring how the acceleration of the apple kind of corresponds to gravity itself. So that's one example. We might also have something a bit like this. So we've seen something similar. We saw that radioactive decay where we've got a decline in the number of particles over time. Here we're talking about cooling of a cup of tea. So in this case, we're interested in how does the temperature, capital T, change with respect to time. And this is a simple law of cooling. Again, there might be other things going on. But we've got a couple of parameters here. So we've got our heat transfer rate. So you can see that's going to affect the rate of decline in the temperature of the tea. And then we've got an external temperature as well. So with the radioactive decay, if you remember the graph, it started with a steep decline and then leveled off. but it was approaching 0. In this case, we're never going to reach 0. We're going to approach, eventually, the external temperature. So the T is only going to cool down as much as the room temperature is in. Okay. And then a couple of other examples that we're going to spend a bit more time on, and you're going to see a bit more in kind of the practicals and going forward with some of the other models, are around population growth. Okay. So we've got 2 here. Let's start with this one. Hopefully it's visible. So we've got the n by dt is equal to some parameter r, which is our growth rate, and our number of bacteria in this case. So here we've got a population of bacteria. We're interested in how that population of bacteria changes with respect to t, or time. And our first model is to say that, okay, the number of bacteria and how they change over time is proportional to the number of bacteria itself. So the rate of change of our population depends on the size of the population. So if you start thinking about, okay, what does that mean? If I've got a small population of bacteria, my rate of change is going to be small. So if I start with a small number, we're going to see an increase, because this is positive, but it's going to be a gentle gradient. It's not going to be too steep. As my population gets larger, the rate of change of my population will also get larger. So you can see we'll start small from a small number, and then we'll ramp up with a steeper gradient. Okay. So that's one population model, and I mentioned bacteria because that captures some of the dynamics we might be interested for some bacteria. But if you think about that, as my population of bacteria gets really massive, so does the rate of change. We'll just keep going and going. We'll just keep growing. That might not be realistic to the system that you're interested in. So you might like to consider another model, and we'll spend a lot of time on this one. This model says, initially, something very similar. So we've still got the same format as over here. We've got dn by dt proportional to Rn. But we've also got this extra term in the brackets. So here we've got another parameter. That's our carrying capacity. We'll come back to what that is. But it's trying to capture the idea that we don't have a population growing indefinitely. We've got something limiting how big that population can get. So let's think about this. If n is small, this term is quite small. So this whole thing in the brackets is about 1. We're talking about very small n at the moment. So if n is small, we can sort of ignore these brackets, and we get a similar equation to what we had before. So we start increasing the population size. As n gets towards our carrying capacity k, this term, n over k, gets closer to 1. Which means that 1 minus 1, essentially 0, and our rate of change becomes quite small. So initially, when our population n is small, we've got that increase. It looks like this equation. But as we approach our carrying capacity, this term in the brackets gets closer to 0, and our rate of change gets closer to 0. So as we approach our carrying capacity, our rate of change is slowing down. We will have figures for all of this. It's more just thinking about, okay, if we've got a differential equation like this, what can we say about what it might look like if n is very big, or n is very small, or time is going on? Okay. Our final example, and we will have plenty of time on this, especially through the course of today, is a model of an infectious disease. So here we've got our population split into 3 different groups. I've said susceptible people or infected people, but this could be animals, could be vectors. Here we're interested in how the number of infected people changes with respect to time. So we're thinking about di by dt. If we look at this figure on its own, we've got something increasing the number of infected people and something decreasing the number of infected people. So people enter the infected class when they get infected, transmission occurs, and they exit the infected class when they recover, in this case. So we've got two terms in our differential equation. We've got an infection term, and we've got a recovery term as well. Don't worry, we will definitely be going over this, what these mean, and what do we mean about contact rate or recovery rate, and what that translates to in terms of behaviour of this. But this is just to show different types of differential equations so you get used to recognising them. Okay, so I've just thrown a few differential equations up on the board, but it might seem that they're a bit abstract. Why would we even get to that point with our differential equations? So we wanted to talk a bit on the modelling process itself. And this kind of pathway is the sort of thing that we'd be thinking about. So often, okay, let's think of a scenario. So you're working with a different group. You're doing a model, maybe a policymaker has got a question for you. So you talk to them, you try and understand what their question is, and then you try and translate it into a mathematical model. And I should note, not everything translates into a mathematical modelling question, that's for sure. So you start with reality, you start with the question that the policymaker has got. The temptation is to say, we know reality is really complicated, all of it's important, so we should capture everything. But the problem with that is, if you've got an extremely, well, firstly, it's tricky to put the model together, and if you capture everything, it would be massive. And then the other thing is, if you start running and exploring that model, computation time aside, it's quite difficult to unpack what it's telling you. If you see a change in some population, is it due to this factor or that factor? It's difficult to unpack. So even if you go through this process of reality to a mathematical model, you want to start simple and then build up. You want to focus on going back to that question that you've got from the policymaker or your research question and thinking about, okay, which bits are really essential for me to capture in my model? What can I inform by data? What information do I have? And then use that to refine your question, think about an abstraction of reality. You can write down any assumptions or limitations of your model, but that should give you a model that when you start exploring the behaviour of it, or you start simulating or providing results, you've got a good feeling for what's motivating those results. So what are the mechanisms feeding into everything that I'm interested in? So if we start with reality, we've got this apple, it's perfectly rendered, we've got an apple falling from a tree, it might be affected by wind speed or other factors that day, whether a bird flies into it, that kind of thing. But we might only be interested in when is it going to hit the ground on average. So at that point, we're just really interested in the position of the apple. It doesn't matter that it's green. That's not something that we have to capture with our model because we're interested in its position. So we take our apple, we abstract it, focus on the key bits of information, and then define our mathematical model with the proviso that it doesn't capture that the apple is green. And that's okay for this problem. So that's one way of constructing. Hopefully at that point you've got a model that you can explore, you can look at the dynamics, you can see how it's changing, you can simulate it, maybe say, okay, well, 2 hours has elapsed, do we think the apple's on the floor yet? We can work that out with our model. That should give us some insight about our abstraction, and then hopefully that's useful for reality. I've got this over 2 slides, but in a real-world situation, this is kind of a loop, right? Hopefully, when you start with your research question, you abstract it, you think about the model, you do something with the model, you bring it back to reality or your data set, and you say, okay, how well is my model doing in capturing the insight that I need from it? So you might have a few loops of this, a good few iterations to refine your model. So I mentioned if we've got a model, we can start exploring its behavior, seeing what it looks like, and we might solve it. And by solve, I mean solve it analytically. Can we write down the solution ourselves? Or we might simulate it using a computer. If we're solving it, we can do that for certain simple differential equations. You'll see that quickly it gets a little bit more complex when we start to solve things analytically. And often, by the time we've got a model that captures the dynamics we're interested in, we've probably got something that we just want to simulate. But let's go through some steps. Sure. Hello.
Yeah, I just want to know how you pronounce or how you say the previous term. Like this is the rate of change of y over time t, right? The one you just. So, but this one, when you have d squared and t squared, how do you say it?
I think there's a few different ways of saying it. I mean, I'd be tempted to say second derivative of x with respect to t. And then that's, if you wanted to get onto the third derivative, it follows. So I would describe this as second derivative of x with respect to t. I think in the slides yesterday, we had a shorter notation where it was y prime, so you have a dash. So you can do the same thing, you can have y double prime. It's a quicker way of writing it, but if your handwriting is as bad as mine, having a dash is easy to miss. So I'd be tempted to write it like this so it's a bit clearer. But yeah, I'd say second derivative. Okay. Hi.
Yes, then what would be the similarity or how they be? If you get the derivative 1, derivative 2, derivative 3, how much do they differ? Are they same?
Depends on the function. If we've got, so the question was, if we've got second derivative, third derivative, are they the same? Are they similar? If we're differentiating an exponential function, yeah. But that's a special case of the exponential function. For the most part, every time we differentiate, we get a new or another function. So if you think about when we were differentiating x squared, we got that straight line as the derivative. If we differentiated our straight line again, we just get a constant. So we're going from one function to another function. They are getting simpler in that case. It doesn't always play out like that. But generally, every time we differentiate, we get another function. But it varies by what we start with.
If you do it again, that's when it becomes the second derivative.
Yes. Yeah. Yeah. So what's going on here is we started with x as a function of t. We differentiated it once. And we got something that looks more like this. And then if you differentiate again, that's when you get your d2y by dt squared, or the second derivative. Okay. I've got to say that we're not really going to be wrestling with second derivatives in this course, but it's useful to see some of them, especially when we're talking about acceleration. It's a nice example. Sorry, did you have your hand up?
Do you also calculate the second derivative?
Yeah, so you can start, if you've got nice second order differential equations, you can start solving them. So yeah, there's a bit of rearranging and then you're integrating. We're not going to do too much of that because often with epidemiological models, the first derivative is what we're interested in. But yeah, you can start solving them. It does have to be quite a nice one of a specific set of formats. But yeah. Great. Okay, so we're going to go through some examples of solving differential equations like this. So starting with here, we've got dy by dt is equal to 2, so just a constant. So our rate of change is constant. We can integrate this. So we've got here y is indefinite integral of 2 dt. So we're integrating with respect to t. That's all this term is saying. And when we integrate a constant, we get our linear equation, so 2t plus our constant of integration. So we've got an indefinite integral, so we include our constant of integration. How do we get a value for this c? Well, that's where I mentioned yesterday that when you try and solve these, you do need an extra piece of information. Often, the extra piece of information you have is, what is my starting population? What is my starting condition? So when you see these solutions, they'll say, okay, we've got our differential equation, we've got initial conditions. So what is y of 0? So if we've got a value for y at 0, our starting condition, then we can put it into our new equation and solve for c. So our constant of integration is our initial condition for y. Everyone happy so far?
Yeah.
Great. Okay. There are lots of different ways to solve differential equations. They've all got different names, like different methodologies. You can do things like separation of variables. We'll look at an example of that. But there's a whole bunch of things. So integrating factor form, auxiliary equations. We're not going to go through all of these. We're going to stick with one example, give you a feel for solving a differential equation. But then you'll see by the time we've got onto this, in terms of a modelling equation, it's still not complex enough to capture the things that we're interested in. So at that point, we're probably going to jump to simulating it in the computer. So yes, we've got lots of methods, but they generally work for simple differential equations. So let's look at a couple of other examples. So we've looked at this, and we've solved it. It was nice. We've got our differential equation. Our rate of change of y with respect to t is a constant. So we've got a constant rate of change. On this one, we've got something slightly more complex. What we're saying here is the rate of change varies by time, if t is time. And then this final one is something a bit like what we were seeing earlier. We've got our rate of change of y with respect to t is proportional to y itself. Okay. So it's always good to define your variables. It helps you think about what are we actually measuring here. So I've slipped into saying that t is time, but it could be something else. And it's useful to think about the units. So again, if you're thinking about time, are we talking about a change in days, or are we changing every year? That will affect how we estimate our parameters, potentially. Okay. So we've gone through, we've solved this one. It's a nice one. We can just integrate it. Got an indefinite integral, our constant of integration. Then we solved that using some initial conditions that we were given as well. So in this case, let's say that y is a number of ducks. We've got a population of ducks that we're interested in modelling, and t is the time in years. Given that context, what we're saying with this equation is that every year, our number of ducks increases by 2. So our rate of change is constant. What does it look like? Well, we've solved it, we've integrated, and we've got a nice straight line. And here we've got multiple straight lines because we might have a different initial condition or a different initial number of ducks. The blue line is saying that we started with no ducks, and then every year we got 2 more ducks. If we're talking about a closed lake where you are adding ducks manually, this might be a good model. But for anything where you want to capture some change over time or some change with the population, this might not perform so well. Okay. We can do a general form of this. So if our dy by dt was just alpha, so alpha here is a constant, just a number, we can integrate it in the same way. Indefinite integral, we have our constant of integration, and here we're going to start from 0 again. So if we've got initial condition at 0, that gives us our constant c. And then we can look at how that changes over time. So that alpha, which hopefully is visible, just gives you that gradient on that straight line. So it's the starting point for the modelling. It might not be the best model for your particular question. Okay. Let's do something slightly more complex. Here we're saying that our rate of change depends on time. So every year, as t changes, we're seeing a different rate of change in our population size. So it's a little bit more complex. We can still integrate this straight up. Got our indefinite integral. We're integrating 2t, so that goes to t squared. And then we solve for our initial conditions or some condition. This looks a bit more interesting. So as time goes on, our rate of change is increasing. So you can see it's slow to begin with, and then the gradient's increasing. We've got multiple lines because we've got different potential starting points, but you can see they all follow the same trend.
And that is the more realistic model, right? That occupation will change differently according to time points in real life.
In real life,
Yeah.
this might look a lot like your data, and this might be sufficient to capture some of the data or the question that you're interested in. If you're thinking about the mechanism here, so we're saying the rate of change only depends on time, but there might be other factors that we then want to capture. So the next model might be a slightly more realistic one, but it depends on your question. So every time you add complexity to your model, you might be capturing a new thing about your problem, but it comes with a cost. You've got to be able to justify that complexity as well. Okay. So, final one we're going to look at with this example is one where our rate of change of our population depends on the population itself. So if we've got no ducks, we've got no rate of change. Nothing happens. If we've got a large number of ducks, here we're saying that the rate of change of the number of ducks increases. Okay. So here we're capturing something called exponential growth. We've already seen this for the bacteria, and maybe this is enough complexity to capture your data. It looks very similar to the other differential equations that we looked at. So rather than having t, we've got y here, but now we've got to take a slightly different approach for solving it, because we've got y on one side and we've got our differential equation, our differential there. This is a separable differential equation. So we can take an approach like this. So this comes from reverse chain rule. When you look in the zip file or the folder, we've got a bit of background on why this works. But if you remember yesterday when we had our differentiation lecture, we had something called chain rule, where you've got a function in a function, and how to differentiate that. We can do something like the opposite of that relationship to be able to solve our differential equation here. So what we're thinking about is we're trying to get y on its own, and we're trying to get t on its own. That's what we mean by separable differential equation. If we take y over the other side, so we've got y dy by dt, then that's the point where we can use reverse chain rule. And as I said, there is a handout that goes through those steps. Okay. So we've got y on its own, we've got t on its own, and now we can start integrating. Note that here we've got our indefinite integral with respect to y, and on the other side we've got our indefinite integral with respect to t. Okay. We know from some of the rules that we saw yesterday that if you integrate 1 over y, you get natural log of y. So this is log base e of y. And over on the right-hand side, we're integrating a constant. So we get 2t, and then we've got our constant of integration. Really, both of these integrals will have a constant. But just for convenience, we've decided to put the constant together on one side. But there will be a constant coming out of both of these integrations. Okay. So now we've got an equation using a log. So yesterday we looked at solving equations with logs in. And the first step is to try and rearrange it so the log is on its own and everything else is on the other side of the equality. We've already got that. So this is the point where we can take our exponentials. Okay. So we've got log base e here. We take our exponential and we've got y is equal to e to the 2t plus c. And the final bit, really we can stop there, but we like tidying up terms and things. So we can use the fact that if you've got e to the something plus something, we can rewrite that as e to the something times e to the other thing. C is just a constant, it's just a number, so e to the c is also just a number. So we can rewrite it to look a bit like this. So this is our e to the c, we rewrite it as a. A is just a number. Okay. So we started with our differential equation. Essentially we're saying the rate of change of ducks depends on the number of ducks. It's already complex enough that we want to take a slightly different approach to solving it, but we can do, because it's a separable differential equation. And once we do, we get this nice equation for the number of ducks at time t. So we've got exponential growth going on. And we'll come back to, in a moment, what that looks like. So we've got a here. Again, that's just e to the c, it's just a number. And in the same way as we did with the other differential equations, if we've got another piece of information, an initial condition or a starting point, we can figure out what a is. So if we know what y was at the beginning of the time series, what our initial condition is, then we can rearrange this to solve a. Okay. So we've got our equation. We're going to say we know what the initial condition was when t equals 0. So if we put t equals 0 in, we get e to the 2 times 0. That's here. E to the 0 is 1. That's one of our rules. So our a is just whatever our initial condition was. So we've solved for our constant. And that means we've got our final equation for y, the number of ducks, in terms of time. Okay. What does it look like? Well, if we start from, we're starting actually from 1 or so here. We've got a slow initial growth. Again, thinking about what this equation is saying, if we've got a small number of ducks, if y is small, then this initial growth rate is also going to be small. So it's a gentle gradient here. But as our population gets larger, this rate of change also gets larger. So we really ramp up. Okay. These different lines have a different y0. So we're starting at slightly different places at the beginning. But you can see, because y0 is timesing this whole term, that does affect these lines later on. It's clear to see how they split up. Okay, sure.
Can you kind of explain the difference between the growth rate and the rate of change?
Rate of change and growth rates. It's a good point. So I've been using rate of change kind of to capture this part, so the differential. So here we're saying, okay, how is y changing with respect to t? What's our rate of change from that? But you're right, we do have parameters that are defined as the growth rate. So we had that bacteria population, we had R, that we call the growth rate It's a parameter. As you can see with this, we've got y0, we've got a parameter in our model, and that's affecting how these lines look as time goes on. So I think I've been using it, rate of change, to capture what I mean by differentiating y with respect to t, because often when we're thinking about a change with respect to time, we're talking about a rate, but there's also parameters that we define as rates. We will go through different parameters and how they might come about in a SIR model, an epidemiological model, I think after the practical this afternoon. So we can come back to that question a bit there, I think. Great. So we've got a model for our number of ducks. Again, this might be enough to capture up the behavior of our system. Maybe we've got a time series that lasts 2 years and we've seen exponential growth in that time, and that's what we want to capture with our model. If you expanded this time series, if we went to 50 years, we could have a huge number of ducks and they'd be growing rapidly. So maybe it's not the best model if we've got a different time window. Depends on your question. We've got a general form of how this might look. So if we've got a differential equation where we've got beta, beta is just a constant, just a number. In the previous example, it was 2, but it could be anything. We can solve this again and maybe start with an initial condition of 1. So y0 here is 1. And then this figure just shows different values of beta and how they might look in our solution. So if we've got beta is positive, we've got that exponential growth, same as before. If beta is negative, we've got exponential decay. And that happens initially fast because it's based on our population size, and then it gets slower as our population gets smaller. And we might have this slightly boring example of beta equal to 0, which is just a flat line. So we can get quite different behavior for different values of that constant beta, just that number, from the same differential equation. So we've looked at differential equations. We've looked at a bit of the modeling process. So you start with a question. A policymaker comes to you and says, I want to know how many ducks I'm going to have on my lake in 3 years' time. You know there's lots of things that you could include in that, you know, the type of duck, the size of the lake, but really they only want to know that number in 3 years' time, so you put together the simplest model you can do to capture that question. You look at the data, see how your model is performing, and then iterate to get a better model. You can do the same things with building models of populations in general. So here we're thinking about how is our population N changing with respect to time. We might have things that increase our population, so things like births or immigration, and we might have things that decrease our population over time, so things like deaths, emigration, predation is a special form of kind of death. So you can add different terms to your system to capture some of these factors that you might find important, and consider how they will change your particular variable or your particular population. So let's start with something that looks a bit like this. So here I've got my population N. I'm thinking about how it changes over time. And I've got some different terms in my equation for it. So this first term is a constant. So alpha, just a number, it's a constant. What does this sort of capture? Well, we had an example like this for our ducks. If we just think about that on its own, here we're saying that the rate of change of our population that was dramatic. Okay. Here we're saying the rate of change of our population is affected by this constant. So this might be a good way of capturing things that don't depend on your population, they don't depend on time. So maybe every year we're expecting 2 ducks to enter your population, and then this constant term is enough to capture that. We might have something slightly more complex. So here we've got a linear term in n in our population. So now we're saying that the rate of change of n with respect to t also depends on the population at that time. So we'd say this is a population-dependent effect. So an example of this is simple births or deaths. So we'll be looking at examples of simple birth and death in the SIR model, I think this afternoon. But we're saying the rate of change depends on the population itself. Final thing is something where we've got, oh, this is tricky to read, but we've got 2 terms here. We've got some parameter gamma, it's just a constant, it's just a number. And then we've got n and m. So here we're saying that our rate of change of n with respect to t depends on the population itself, but also some other population. So we might use something like this to capture competition between different species, or we might have something like this for a predator-prey model. Okay. So for your particular problem, or your population, you might want to think about which of these types of terms is most appropriate for the thing you're trying to capture. Sorry, go on.
So the last term, I would like to know how did you come up with, n multiplies by like you are explaining a biological system, something that is happening.
Yeah.
So how do we, based on what is happening, switch to, how do we come up with this, multiplication based on the biological system, something that is happening in this system? Yes.
So yeah, great point. How do we come up with this term just multiplying together? So we do have, I think, as the very next lecture, we go through a predator-prey model. So we're going to go through how prey might affect the predators and predators might affect the prey. You're also going to have an example in the practicals. What we're saying here is, so in this case, we've got something quite positive going on. So as the rate of change of n with respect to t depends on gamma, n, and m. If n is larger, we've got a larger rate of change, so it's increasing. If m is larger, so they're boosting each other in this particular case, just because we've got it positive. But yeah, in the next lecture, we'll go through step by step how we put that together for a predator-prey model. Hopefully that helps. Do you want to go first and then come to you?
Okay. Can I just shout? So maybe. I'm just curious before I forget. Is of course you have you have an equation describing how n changes over time, but I think is it an acceptable standard in mathematical modeling to start in a very simplistic manner?
Yes, please. Start simple. Definitely.
Okay. And then the next question is based on whatever you build or whatever assumptions you make. Is it something that you have to justify based on a parameter-based?
Definitely.
Okay.
So, yeah, definitely starting simple. You can set up your code, your model that way, and you know exactly what's affecting what if you've got a very simple model. You can then add complexity. As you add new terms, you can see what that term individually is doing to your model dynamics. So that's great for making sure that you've coded everything right, it's doing what you expect it to. For each layer of complexity you add, you're going to need some justification. Either you've designed your model and it's not capturing a key component of your input data, so then you have to go back and refine it and say, what mechanism am I missing? I'll add that complexity. If you add too much complexity at once, it's difficult to untangle which bit is driving what. So definitely starting simple will help with the justification of adding complexity later on as well.
Oh.
Go ahead.
Yeah, so I see that equation has one constant, but then the gamma there, and you call it a constant as well.
Yeah.
Is it just a number?
It's just a number. So here, alpha, beta, and gamma are parameters, constants in your model. This whole term, alpha on its own, is a constant term, just because we don't have any dependence on n or m. But we do have other parameters, gamma, beta, and alpha through this. This is just pulling together terms. It will be better when we've got a particular thing that we're modeling. Again, it's defining your units, it's defining your terms. Here is just kind of a theoretical pulling together of terms. Okay, so yeah, we've looked at solving them. We got to quite a simple model where we've got exponential growth, and we could solve that. That was fine. But you can imagine as we keep adding layers of complexity, it gets trickier and trickier to solve analytically. So that might be the point where we start jumping to simulation. Going back to our really simple example where the rate of change of y with respect to t just is a constant, t, and using this initial condition, y equals 0 when t equals 0, that extra piece of information, we can start simulating what our model looks like. You will be doing this in your practicals. This is a very exciting graph of a straight line, but you can see later on how you'd start putting this into R and starting to simulate yourself. What are we doing with that? Just very briefly, if you remember yesterday when we had our definition of a differential, of a derivative, we were sort of thinking about approximating the tangent line, so the line that only touches at one point. We could think about the derivative of that point as approximated by that tangent line. So the way we did that in some of the examples on the differentiation lecture is we took one point and another point on the x-axis, just a little bit further along, and looked at trying to estimate the gradient of the line at that point. As we moved these 2 points together, so in this case, as delta t gets smaller and smaller, this approximation, this straight line, becomes a much better approximation of our yellow curve. In your computer, it will be doing something similar, maybe not quite this method. Methods have improved, and the reason they've improved is because as we do this approach, obviously there's a bit of an error between our straight line and our curve. So from what we predict by using this method, and then the actual y there as well. But essentially, with some variations, your computer is going back to that definition of a derivative and then using that to approximate how your differential equation changes for each time step. Like with the proofs, we're not going to look at this from first principles. We're just going to start using simulation in R ourselves. So we've gone through some differential equations. They're great because they capture some information on how one variable is changing with respect to another. And then we can start using them to build up abstractions of reality or try to get some insight about a real-world problem. We started solving them, but very quickly it becomes not feasible, intractable, takes too long to solve analytically, so we start simulating them. That's what you'll be doing in the practical. And the aim of doing that is so that they give you some insight on your abstracted system. Okay, so any questions on differential equations at the moment? I'm wondering if we have a 5-minute break before going into the next lecture. Yeah? Great. Okay. So if we start again at 9:50, it's a bit more than a 5-minute break. All right? So Okay, so I think we'll start on the next lecture, interacting populations. So this will go through some of that problem where we've got one population depending on another, and we're going to go through how we put together the terms of the equations for both of those populations to capture that relationship. We're going to make sure that we finish on time for coffee, because coffee is very important, and that will fuel you through the practical where you're going to explore some of this yourself. Okay, so we had this on the previous slide deck. Essentially, we want to capture different things that might either increase our population or decrease it. So births and immigration are going to increase our population size, and things like deaths are going to decrease our population size. So all of these are going to have some effect on the equation that we end up writing for our population. So again, we're thinking about adding terms to describe things that affect the variable of interest of population. We've got a couple of examples that we've looked at. Firstly, exponential growth. So here's an example of the world population in billions. You can see that it started with a slow rate of increase, and then over time that rate of increase increased. So it got faster, it changed more quickly as we went over time because the population increased. That's exponential growth. We've also seen this equation, which we call logistic growth. So it looks very similar if we ignore the thing in brackets. So we get exponential growth again. But this also has this extra term where we're saying that as we approach a carrying capacity K, our growth is going to slow down. So we start in a very similar way. We start with exponential growth. The rate of change is slow, and then we increase. But in our logistic growth equation, as we approach our carrying capacity K, this dotted line, our rate of change slows down. Okay. So this might capture that there's some limitation on the environment for the thing that you're trying to model. Your population cannot grow indefinitely. Okay. So these are just terms for growth rate ideas for one population at a time. But we already started talking about you might have impact from one population on another. So you might have two species competing for the same resources. So if one of those populations is very large, it's going to negatively impact the other population. They'll outcompete them. We might have predation going on, so a little mouse eating a scorpion. Here, this is beneficial for the mouse because it's getting some food, but not so great for the scorpion. So they've got an interrelationship with their two populations. And then we've got other weird interactions like parasitism, or we might have things where it's mutually beneficial for two populations to live together, and that's something like the term we had on the previous lecture. Okay, so it's often not quite the case that we consider one population on its own. There might be other populations that we need to take into account if we can justify the complexity. So here's some dynamics that we might like to capture. So here we've got population density, and we might be wanting to follow the predator, which is our bottom line, and prey. So perhaps this is the data that we're given. We're given a time series of the number of both of our species. And we can see that the prey peaks in number and then starts declining, and it's got this nice oscillation. And the predator follows that oscillation, but with maybe a lag. So if we looked at our time series, we might think, there's something relating one species to another. Maybe these are interacting populations. Okay. So the way we capture this in our model is by having what we call a coupled differential set of equations. So it's essentially saying that when we write our equation for dn by dt, it's a function of n, the population itself, another population which we'll call p, and time. And then our equation for P is a function, G, of N, the other population, the prey, P itself, and T. So we've linked these two equations to each other. Okay. What we're going to look through is a particular example of a predator-prey system, and then look at some mathematical techniques for getting a feel for how that system behaves. So even before we get onto solving it, which you will, we'll think about how can we explore the dynamics of our equations that we've set up. And then we'll get onto some computational techniques. So you will have practical on this so that you can work through and look at it in your own at your own pace and explore different things you might be interested in. But let's start building our equations. So we are interested in a system of bacteria and amoeba. We're going to start with the bacteria, and then we're going to start thinking about how the bacteria might be affected by the amoeba, and then thinking about how the amoeba might be affected by the bacteria. So let's start simple and add terms as we think they're necessary. So if we ignore the amoeba completely and we think about the bacteria on its own, well, we've got a population in isolation, so we can define an equation that captures the growth of that population. Here, we're going to use the logistic equation, so the one that goes initially slowly, increases, and then reaches a carrying capacity. That's what this curve is going to give us. This equation is going to give us. We've got a couple of parameters here, and I'm going to define my parameters. We've got a constant per capita growth rate, R, so that's our parameter here. And then we've got a carrying capacity due to limited resources, limited scope. Essentially, as our population size for the bacteria reaches this carrying capacity, the rate goes to 0, so we never quite hit it. So we start with the population and how it might behave in isolation. And then we can start thinking about how we add the interaction terms. Okay. Let's do the same thing for the amoeba and then bring in the interaction of the two. Sorry, go on.
Sorry, I wanted to ask a bit earlier, what does that carrying capacity mean? You talked about nutrition, would there be requirements of the space and maybe some other constricting factors, physical constricting factors? I just wanted to understand.
Yeah. So a lot of the things you listed might affect your carrying capacity. It might be that, well, for bacteria in a Petri disk, it's easy to imagine. You've got space limitations and you've got a certain amount of food. So if the population gets too large, then we'd expect that population to limit its growth essentially, and maybe even start, if it exceeds its resources, it will start dying back. So our carrying capacity there, whilst it's a strange parameter to define, thinking about a number of individuals that a space or a food source will sustain, it's essentially to capture that behaviour that we don't have continuous growth. So perhaps in your lab, you might be experimenting and looking at population sizes for bacteria, and you can start to estimate your carrying capacity. There'll be a bit of uncertainty. It depends how that particular population may be growing. But that's what it's trying to capture, that there is some limitation to what the population can reach in terms of size for lots of different reasons, really. Okay, so we'll do the same process for the amoeba. Here we're talking about predator. We're going to think about the situation where the amoeba's only got one food source, and that's the bacteria. So if we consider what the dynamics look like for the predator without its food source, we're just going to get a decline in the population. So here we've got,
Excuse me, can you go back to the previous slide?
yeah?
So this is for the prey. for...
Yeah.
Okay.
Yeah. So this is for the prey. We're going to do the same process for the predator, and then we're going to link them both up. So here we've got a decline. So we've got no food source. We've got exponential decay. So as our population of predators is very large, this rate will be fast. We'll get fast decay. And then as the population gets smaller, that rate of change will slow. Sorry, go on.
Yeah, so till now we're not, there is no link between the two equations, right?
Yeah.
But for this, why are we only taking into account the decreasing part of the population? The population is not increasing.
Sorry? The last part.
The population.
Yeah.
So, right. So why are we only taking into account the fact that the population of the
predator
is decreasing? Because I think over time there will be new birth, right, in the population.
So yeah, this is the simplification in this model. So what we're saying here is we're expecting that given zero food, in the complete absence of its only food source, we're going to see a decline in the population. In reality, you might have predation of one on another, which might sustain things. It might be a bit more complex than this, but we're starting with our simple assumption that in the absence of our bacteria, our main food source, the population of predators is just going to decline. Okay, so far we've got two equations, they're not linked. So we can start bringing them together. So again, we've got our bacteria population up here and our amoeba population here. So the amoeba are going to be eating or predating on the bacteria. So far, we've had these terms. We've thought about what the population is going to do without the other one. So for the bacteria, this is looking good. They're just going to grow to their carrying capacity and stay there. For the amoeba, they're essentially going to die out. So let's think about these interacting terms. Here, if we introduce a predator, it's going to negatively impact the bacteria population size. So we might have some parameter A, just a constant, and then we're going to have this multiplicative term. So one population is affecting the other. If we've got a large number of predators, you can see this term will get larger. We'll have more predation. Population will decrease. Similarly, if we've got lots of prey, but the corresponding size of both is going to affect this whole term. On the flip side, for the predator, having the prey about is a great thing because then they've got a food source. So we've got a positive term here. We've got a constant B, just a number, and then we've got this interacting term again. So the populations are multiplied together. If there's lots of prey, this is great. They've got lots of food. And we see growth here. A and B might be linked, these two constants, but we're not saying they're the same here. There might be some loss of energy when a predator eats a prey. It doesn't directly mean that we get a perfect kind of one prey loss is one predator gained. We're not saying that. We're saying these could be different in our model. So we started with our populations. We thought about them in isolation. So what does it look like for the bacteria or the amoeba? And then we thought about interacting terms, but we're not saying too much about the constants or the parameters as yet. Okay.
Sorry?
Yeah.
Yeah, so it's well explained, but I only want to understand it intuitively. Like, why are we multiplying M and P? Is it because the prey and then the predator, they are coming into contact?
Exactly. And we can get fancier about this. So later on, we'll come back to SIR models with demography, and we'll start thinking about structures. And we'll come to the idea of you can come into contact with different species or people, depending on your model, and that contact rate might differ. Here we're just saying predator meets a prey. In that scenario, it's bad for the prey, it's good for the predator, but we can definitely have more complex assumptions around that.
Oh, okay. That's why there's a minus there, a plus there.
Yeah, yeah. Overall, bad for the bacteria, good for the predator.
Yeah, so the constants A and B, must there be a constant there?
So here, what we're doing is giving ourselves the flexibility in our model to explore different values of A and B. It might be that we fit this model to data, we compare it to what we know, and it might be that A and B are both 1. But we're giving ourselves the flexibility there.
Adjusted.
Yeah.
So it's more like allowing us to fit the model to the data.
Yeah. Yeah. So flexibility is a good thing, but if you've got too much flexibility, it can mean that when you come to fit it, you've got one thing that's moving up while another is moving down, and you get the same. That's a fitting thing. We'll come back to questions like this. But essentially, writing out these equations, what we're saying is there could be some kind of parameter A and some parameter B. We're not saying what they are yet. They could be 1, but it's giving us that flexibility. So here we've got our set of coupled differential equations. One equation depends on the population in the other one. That's what we're saying. Can't solve them independently because they're now linked. So we have to use other methods to explore what's going on. One way we could do this is by phase diagrams. This is something, I mean, you'll be looking at this in the practical. It hopefully will give you some understanding about how one population is changing as another changes. So now we're thinking, rather than looking over time, we're thinking about how the size of the predator population changes as the size of the prey population changes. As you can imagine, if you've got more than 2 populations, making a graph like this, not so helpful, not so feasible. But for this lecture, we're going to explore what this behavior looks like to give you a bit of insight on the simple system so that when you start building more complex systems, you've got a feel for what's going on behind the scenes. Okay, so here we've got a graph. We've got N, our prey along the bottom, and then we've got our predator along the side, and we're thinking about how the trajectory, how one population is changing as another changes. Okay. This is maybe easier to think about if we compare it to the graph over time. So here, we've got how both of these populations, N and P, are changing with respect to time. Let's have a look. So here, if we start from the top, we've got this blue line, that's our prey. We start with 100, a high population size, but we've got some predators in the population. So we know the predators are going to start eating the prey. So over time, we see a decline in the number of prey because they're getting eaten. There comes a point here where the predator, their population size has grown because they've been eating the prey, and now they're eating too much. They're running out of food. So the predator population has grown beyond the resources available in terms of the prey population. So their population size peaks, and they start to decline. If the predator population size is getting smaller, that's good for the prey. They've got fewer predators. So their population size starts to recover as well. They can start growing again. So you can see we kind of get a decrease, we get some oscillations, and then we're trending towards some sort of balance. In this balance, or equilibrium, we've got just enough birth going on in the prey population to balance all of the prey that are getting eaten by the predators. Okay.
I have a question.
Yeah.
Are these assumptions based on the fact that the predators and the prey, they are in an isolated environment? Because if that is not being considered, the fact that there are other predators in the environment makes the prey vulnerable to other predators. And the predators itself we are considering here might not be the one actually feeding on those prey, but
Yeah.
If there's an assumption that they're in an isolated environment and just the two of them are there, then I think all this holds.
Yeah. So, limitations of this model, yes, we are ignoring any other predation. We're also ignoring the idea that the amoeba might eat themselves if they don't have enough prey to go around. So, in this very isolated system, which might be enough for the problem, we've only got one predator, one prey, and that's it. But yeah, you're right. Yeah. Okay. So, that's what it looks like over time. What does it look like in this phase plane? So again, we're starting with a high number of prey and a low number of predators on the y-axis. What we're saying is, okay, so we've got a high number of prey, great for the predators, they start eating lots of prey, so the population size of the predators starts to increase, and the population size of the prey decreases. Okay. We reach a point though, where the predator population is so big and the prey population is now too small to sustain that number of predators. They're running out of food. So we reach a turning point. At this point, the number of predators, if we think about what's going on in the y-axis, number of predators decreases. They're running out of food. And we might see a turning point where the prey population starts to recover a bit, so we're over here. That's what we've got going on here. But you can see if we keep running this, so time is moving round this spiral. If we keep running this, we reach a point where we've got just enough prey, just enough birth of the prey to sustain a population of predators. So this is our equilibrium point. So again, this is something that you'll be plotting in the practical, and you can move between the graph where you've got both over time, and then this phase plane where you're looking at how one population changes as another changes.
So it means that both of them describe the same thing?
It means that they're linked in their behavior. So as one population is changing, that's going to have an impact on the other one,
Yes,
and
I'm
vice
saying
versa.
The
two graphs.
are
Yes.
explaining the same thing.
Yes, what we've got is exactly the same simulation of our model going into both of these. We're just plotting them in slightly different ways. Yeah. Okay. So we might be interested in constructing one of these phase diagrams. Let's say we put together our model of interacting populations. We've made some simplifying assumptions, like they're in an isolated population. We can approximate this by looking at it by hand and thinking about some of the key features. Now, while I mentioned that this is great to do for 2 populations, but in reality you might have 3, 500, a much more complicated system, some of the things that we're going to use when calculating this apply to pretty much any system that you're going to be working with. Okay. So, first thing we would do when constructing one of these or thinking about exploring our model is to find the equilibrium points. What do we mean by that? Well, we mean the point where neither population is changing. So we're thinking about, on the time graph, that flat part where they've reached kind of a stable or steady state. If neither population is changing, then our differential equations we can set to 0. Our rate of change for n with respect to t is 0, and the same for the predator. So, an equilibrium point must satisfy these 2 equations. They must both be 0 at an equilibrium. This is something you'd calculate for many different systems. Okay. So, what does it look like on the phase diagram? Well, it's here. This blue dot, that is our steady state, and that's what we want to look for when we're exploring our equilibrium point. Okay, so how do we do that? Well, we know that the rate of change of both of our populations at the equilibrium is 0. They're not changing. We're at a steady state. Sure. Do you want to go in?
I'm sorry to take us back.
So the phase, I'm not sure I get it right. Just some figure like this, and is that equilibrium point. What is, are we supposed to, how are we supposed to interpret that in terms of what does it say, you know, at that particular point?
Okay.
Yeah.
Yeah, so question is, what is this telling us at a particular equilibrium point, right? Yeah? So the phase diagram, you can see lots of little arrows, we'll come back to that. But here we've got one trajectory. So this is how our model might play out if we start at this point. We get a trajectory in terms of the population size of both. This is how they might change over time. If we started at another place on this graph, we might get a different trajectory. The dynamics might look different because we started with a different number of predators and prey. The equilibrium point, though, is a point where if we started there, we wouldn't move, because the rate of change at this point of both of our populations is 0. So if you brought together bacteria and amoeba in the proportions that match up with this equilibrium point, they wouldn't change, because it's going to be stable. We've got just enough prey being born to sustain the predator population. You can have more than one equilibrium point, and it's good to know what they are. Certainly when we come back to disease models, they can tell us about what is the expected endemic number of infections we might have, and we might have the situation where there's no disease, that's a stable equilibrium. So we might have more than one equilibrium point, but that's quite useful to know because it can tell us some characteristic of our system. I might come back to your question later on when we've got multiple trajectories on this and show you something on that. Okay. So we want to get our equilibrium point. It's the point where the rate of change of both of our populations is 0. So we can set our differential equations to 0 and solve them. This is a case of rearranging. We're not doing integration or differentiation here. So we've got our two equations. Just bringing them up top, exactly the same. And if I check it, yeah. Between this slide and this slide, what I've done is I've just factorized it. So I've taken n outside the brackets, I've taken p outside the brackets. So here, we're going to get 3 equilibrium points. Let's break it down step by step though. Firstly, let's look for the simple ones first. I'll stand this side. Here, we're essentially looking for values of n and p that make these make sense, right? Because we've got an n outside the bracket, if n is 0, that first equation makes sense. Great, we've got a solution for n. We can use n equals 0 and see what value of p makes this equation make sense. Okay. So if n is 0, this whole term disappears, and we've got minus dp is equal to 0. So if n is 0, p is 0, that makes sense. That means that both of these equations are 0. Okay. Let's start here. We've brought p outside the brackets, we've factorized. So if p is 0, it makes sense, this equation. Let's take that and put it in our equation for n. If we do that, p is 0, this term disappears, and we're left with n are 1 minus n over k. We've already looked at the slightly boring solution that n is 0, so let's say, for the sake of argument, that this term disappears, but n is not 0, so this bracket must be 0. That only works if n is equal to k. So if you imagine n is equal to k, this whole term becomes 1, so we've got 1 minus 1, 0. So what are these equilibrium points saying to us? If we've got no populations at all, nothing changes. Very boring. If we've got no predators, the prey population will grow to its carrying capacity and stay there. So that's another equilibrium point. We've got no predators. There is a third equilibrium point, and that's what we saw in the phase diagram. For that, we assume that neither n nor p is equal to 0. Okay. So we do a bit of rearranging. Firstly, because we're assuming n and p are non-zero, we can get rid of these terms. We can divide by them because we're not dividing by 0. If we do that, we end up with this, a bit simpler. We can rearrange this equation to get n on its own. So we do that. We get n is equal to d over b. And then put that back in to this first equation and rearrange for p. So this is solving a pair of simultaneous equations by substitution. You could do it by elimination. I think substitution works a bit nicer. So if we take this value of n, we substitute it into that equation that we got from the p, the predators. We put it in there, and then we rearrange for p. So we've got our 3 equilibrium points, the 3 points in our model where nothing's changing. Either we've got no populations, nothing happens, either we've got no predators and the prey just grows to their carrying capacity, or we've got this balance. So we've got just enough prey being born to sustain the predators in eating them. So that's our equilibrium points. 0, 0, no predators, but we've got prey growing, and then this balance point here. If we start at any one of these points, we're not going to move anywhere else. Okay. So, next up, we've got equilibrium points. That's where both populations aren't changing. So what is going to happen if one of our populations is not changing? So when we reach a maximum or minimum in that population. Well, that's what we call a null cline. So it's similar to an equilibrium point, but we're treating one population at a time. So we're essentially saying, where does our prey population, where's the rate that our derivative equal to 0? And then the same for the predator, where is our derivative for p with respect to time equal to 0? These might not be a parameter, they might be a whole line, and then every time our population crosses that line, we see a change in it. I'll come back to what that looks like though. So it's a bit like an equilibrium point, but we're thinking about each population individually. So we can say, okay, let's start with our prey population. We're wondering what happens or what conditions need to be met for our derivative to be equal to 0. So we set our differential equation equal to 0. We factorize. If we've got an n outside, then n equals 0 is a solution. That's one solution straight up. If n is not equal to 0, then this whole thing needs to be 0. And that only makes sense if we've got p equal to a straight line in n. Okay. So we've set our differential equation to 0. We've rearranged to find our 2 null cline solutions. Okay. We do the same thing for the predators. Again, p null clines satisfy when we've got the derivative equal to 0. So we set the whole differential equation equal to 0. We factorize. P equals 0 is 1. That's straight away from this. If p is not 0, then this whole bracket has to be 0, and that only happens when n is equal to d over b. Okay. So we're doing the same sort of steps of rearranging and solving here. And this might look familiar, as you can probably imagine, where the null clines intersect. That means both of our populations' rate of change is 0, and we've got an equilibrium point. Okay. So we can plot these null clines. We've still got our 3 equilibria points. There we've got 0, 0, prey only, and then this balance one. And you can see the different null lines where they intersect, we get an equilibrium point. So what are they telling us? Well, these are the lines where one of our differential equations is 0. So we're reaching that local maxima or minima. We're seeing a change in the direction for that population. We can think about what that change might look like by thinking about if we cross this line at a particular point, what we might expect. So here we've got a blue null line, so that's a null line in the amoeba. So that's a change in their population, or that change in the rate of change of their population, moving from either increasing to decreasing, or so forth. And we can think about what the other equation might be doing. So if we've got a null line for the amoeba, what is the bacteria population doing there? So the way you can do this is for your model, you could put some numeric values in. You can see whether it's a positive or negative movement. I've put a few arrows on here. You're going to explore this in the practical and run some trajectories. That's one of the nicest ways to think about adding some trajectories to this figure. Sorry, did you have a question?
So I thought you said the population is not changing, so how is it going more or less of one of
Yeah.
the populations? I didn't understand why we're going, you're assuming it'll never change, like for example, if it's the bacteria population, it would remain the same.
Yeah.
So then how would the amoeba population change then?
Yes. So this is the headache with null lines. When we say one of our populations is not changing, with a null line, the other one could be. So all we're doing when we're solving for a null line is we're setting one differential equation equal to 0. But for this value of n, we might see the prey population still changing. This is why they're a headache. So when we add arrows to this, you can see on the blue lines, we've got horizontal arrows. We're only seeing change in the bacteria population, nothing in the amoeba population. And when we cross the red line, we're only seeing vertical arrows. So only seeing a change in the amoeba population. Here, at this point, we've got lots of prey, and the amoeba population can start growing because we've got a small amoeba population, plenty of food, they start growing. We see a vertical increase. Over here, in contrast, we've got a large amoeba population, not much prey. So when we cross this null line, we're going vertically downwards. But null lines are a headache because with these lines, we're only thinking about one population having a 0 differential equation. It makes more sense to think about these equilibrium points. At these points, yes, both populations have a 0 differential equation. They're not changing. Once you can add a few trajectories and do a few simulations and put them on, hopefully it will become more apparent. But again, null line's a bit of a headache. Helpful for exploring what an equilibrium point is and how your system might behave. As you can imagine, if you've got 3 populations, you can't draw this sort of figure. So it's more the thinking behind it rather than a particular visual.
Sorry? Can you kindly come again on the direction of the arrows?
Yeah. So with these arrows, we're thinking about, okay, one of the populations, we've set the derivative to 0, so that's not changing. But what's happening to the other one? So either we've got horizontal direction going that way or this way. So here, let's look at the blue null line. So this is where the amoeba population is not changing. Here we've got a small amoeba population, fewer predators. So the prey population can start increasing their population size. They're not being eaten as much. If we go up here, so the other side of the equilibrium point, we get the reverse. We've got lots of predators, and we've got our prey population being eaten. So their population size is decreasing. Again, on these points, we're either getting completely flat horizontal movement or on the red null lines, vertical movement, but they are a headache. The equilibrium points are probably more intuitive to think about because at those points, neither population is changing. Okay. Let me add a couple of...
Please, I have a question.
Oh, go on.
Okay, please, in a true life situation,
Yeah.
is it really possible to have an equilibrium point? Because
Yes.
if the predators are always existing and they are feeding on the prey, at a point, the population of the prey keeps diminishing. Even if the birth rate is at a good rate, we assume, there will be a point when the predators might likely be feeding more on the prey and they likely go into extinction. Or, I don't know how the equilibrium point is actually achievable.
No, this is a really good point. There's a couple of things coming up in that. Okay, so firstly, in a real-world system, can you have equilibria? Yes, they might not be very interesting. I mean, the 0-0 equilibria, that's definitely going to be there. So if you've got no populations, you've got nothing going on. This equilibrium, where you've got a balance, might not be stable. So what I mean by that, and I'm going to come back to it later on, is in the system as we've set it up, and when you start simulating it in the practical with its limitations, if you start with a population of bacteria and predators anywhere here, if this is stable, it will swirl inwards to that equilibrium point, if it's globally stable. It means that we'll end up at that equilibrium point, irrespective of where we start. The example you mentioned is where either we don't have this, it doesn't make sense, or it's not stable. So if we start right on it, maybe nothing changes, but in reality, we're going to have other factors coming into play. So chances are this equilibrium point might not be stable, we might not end up there, irrespective of where we start. I've got a figure for that. The other thing that you mentioned was extinction. Ordinary differential equations, as we've got them set up, we're talking about populations that might decline, so we've got exponential decay. In these equations, we're never going to reach 0. We'll have fractions of a bacteria going on. That's not realistic either. We use ordinary differential equations generally when we've got larger populations, so we're not expecting that extinction or what we might call stochastic die-out. When you get onto doing stochastic models, you can have that sort of behavior. So that's another thing that we might explore later on as well. But yeah, that's another limitation of this. When we're going to have fractions of bacteria, we're going to have fractions of amoeba, and we might never completely die out.
Okay.
So do you want to?
So, I'm the one.
Oh, either way.
Okay. So my question is, for equilibrium points, of course, we equate both of the differential equations to 0.
Yeah.
With the null lines, you equate one to 0 and see what happens with the other one. Is that it?
Yeah.
Okay. So on the graph as well, I see the amoeba null line as the blue line, but we hold constant the bacteria population. Is that what is happening?
So if on the amoeba null line, it's only the amoeba that's not changing, the bacteria can be changing. We're not holding it constant. These are just example arrows.
Okay. Thank you.
At the x-intercept, we put that as an equilibrium point. So why is the y-intercept not also an equilibrium point as well?
So we've got equilibrium points when a blue line meets a red line. Here we've got a red line meeting a red line. So at this point, we're saying we've got bacteria null line, so the differential equation for them is set to 0. At this point, we've got a bacteria meeting an amoeba null line, so both equations are set to 0, and that's why we've got an equilibrium point here. but not there. Great. Cool. So we've started our phase diagrams. We've thought about equilibrium points and null clines. Whilst drawing these on a graph is not possible for a system of 500 differential equations, thinking about the equilibrium points is useful. And then the last step, it just says entire direction field. What we mean by that is we started adding those little arrows to think about how is one population changing in a region of the phase diagram. And we can do that either by thinking, okay, well, on the null cline, we've only got horizontal or vertical movement. So in this area, we've got something, a mix of the two. So we've got an arrow going like that. Over here, we've got sort of arrows moving like this. So it's a mix of the two between the null clines. In reality, it's nicer to start simulating your model and thinking about, okay, I've got my model set up. I can give it different initial points, so different starting population sizes, and then see what the trajectory looks like when I plot it. Here's one potential starting point. As you can see, we started with bacteria population just above this amoeba null cline. So that's where we had that completely horizontal arrow. So we're seeing an increase. When we cross this null cline for the bacteria, we've got just a vertical movement as we cross that. And so we've got this spiral going around. And every time it hits a null cline, that means we see a slight change in direction in either the bacteria or the amoeba null clines. We started in this place. Previously, we started somewhere over here. We ended up at the same equilibrium point. So this equilibrium point, we could say, is globally stable, because wherever we start in this for given values of our parameters, we end up there, unless we start directly on our two other equilibrium points. So if we've got no populations, nothing happens, and if we've got no predators, nothing happens. Again, you'll get a chance to try this out in the practical. So what does that look like over time? Again, we're showing the same thing but plotted in different ways. We're starting with a certain number of bacteria and amoeba. We've got an initial growth in the bacteria population and the predator. So this is going up. We reach a null cline, and one of them peaks. So here we're seeing a peak in the bacteria. So that's here. And then we start decreasing on the bacteria. The amoeba population is still growing because it's got a bit of time to, bit of a lag there until it reaches its peak here. And then the spiral continues. So every time we reach one of these peaks, that corresponds to crossing a null cline. Okay. So we've got oscillations over time. It's heading towards both being flat. In reality, if this was not in an isolated population, this flat line might not be feasible. But every time we reach a peak here, that's where we're crossing a null cline in this phase diagram. Okay. So another reason why we might be interested in the equilibrium point is we might want to know what is the size of the population we expect at equilibrium. So if this was an infectious disease model, we might want to know the endemic number of infections. What number of infections can we expect to see when we reach our equilibrium point?
Sorry?
Yeah.
To come back on this slide. I just want to come back on. Okay, all right. So I would like you to come back on the null cline. It's still difficult for me to understand. Like the D over B is the one we got from the amoeba population, right?
Yeah.
So why do we put it on the x-axis?
Oh, so this is point D of B. So this vertical line here is where x equals D of B. That's where we've got it there.
I don't get it. Sorry, can we go back
always remember from high school the y equals mx equation. We always remember the y equals mx equation for a straight line, but there's two other equations for a straight line which we forget about, which is the horizontal line and the vertical line, which is the line where all of the points have the same value of x or y. And that's what it is here. So that is the line where all of the x values have the value d over b, and then any y value. Okay. It's just a special case where the gradient is 0. 0, infinity, one of those. Yeah. Does that help?
So in that case, sorry, I'll be taking you back.
That's all right.
Yeah, in that case, the blue line, on the x-axis, that's the bacterial population, and because it stays the same, it's just vertical at that point. It's not moving anywhere. And the y-axis, the red line, is the line that's actually declining.
So here we've got, on the y-axis, we've got this red line. That's a bacteria null line. So here, we've got x equals 0, is that line.
Yeah.
If we've got no bacteria, nothing's changing. So our differential equation will be 0 at that point. Same on here, along the x-axis, so y equals 0. We've got a amoeba null line. If we've got no predators, the rate of change is going to be 0. So that's our two axes. We've got another vertical line for the amoeba. So when the bacteria population is d over b, our rate of change of the amoeba is 0. So we get this vertical null line there as well. So this is the equation x equals d over b. That's our straight line there.
Okay.
And then this slope is a more conventional y equals mx plus c line. Okay. Null lines are a headache. I keep saying it, but they are.
Yeah, I'll ask my question later during the break. Yeah.
I think same here.
Okay. So we can also compute this, which you will. This is part of the practical. This is nice. I mean, you do similar things. Essentially, you're running through different trajectories that allows you to fill in the gaps, which would maybe take a long time by hand, but essentially you can try out things in a computer, run it quickly and see what it looks like. You can also see what the equilibrium points are in that scenario. You can see if they're stable or not. So we might have something like this, where we just run different trajectories. So here we started with a high number of prey, low number of predators, and we simulate our system. Here we started with slightly different population sizes, ended up at the same point, our equilibrium point. But you can run different trajectories just by changing your initial conditions and then simulating it. So you can try out different starting values and see what the dynamics look like. Okay. Because anywhere we start except the two other equilibrium points, when we run it, we end up in the same point. We say this is globally stable. There's other dynamics that we might capture with our equilibrium. This is more interesting. This is commonly what you'll come across. If it wasn't globally stable, we wouldn't go towards that. We'd either go to the situation where both populations die out, or we might go to another equilibrium point where one population dies out. But in this scenario, in this example, this equilibrium point is globally stable. Okay. Essentially, it's saying if we start with any number of predator or prey, as long as both of them are present, we end up here. This model's got limitations, but yeah. Okay, so in summary, we've looked at a pair of coupled differential equations. We had to make some simplifying assumptions to make that work. Rather than thinking about analytical solutions, we started exploring things like equilibrium behavior. So as we run it for a long time, where are we going to end up? Or thinking about what happens when one population is not changing, what's happening with the other population. This will be in the practicals, so definitely ask questions, and hopefully the practicals will give you a chance to try out running some of these simulations. But it is coffee time, so I think maybe have a coffee and we'll come back to any questions, and null clients are a headache, and if you don't like them, that's fair enough. Okay.
Yeah, I think just to add to that, to sort of zoom out, this sort of type of formal analysis, it's the sort of thing, if you were a mathematician, you could spend your whole career doing this, just developing exotic differential equations, finding the fixed points, null clients, analysing the nature of the fixed points. Why are we teaching you about this? Yeah, it's not because we want you to sit an exam, but it's because these things are actually useful as sanity checks for your model. So most of us, when we analyse epidemic models, we code them up, we solve them on a computer. But we need a way then to check that what we're getting makes sense. And if we know what the fixed points are, if we know what the behaviour should be around the fixed points, we can make sure the computer is giving us the right answer. And that's why these are useful skills to learn. It's a bit like eating your vegetables. It's a bit of broccoli. It's not fun. But going through the experience of doing it yourself in the practical will hopefully help to make clearer what these abstract ideas, how they work in practice. So there's really no substitute for trying it and doing it yourself. All right. More thing, the practicals are completely student-led. Yeah, so I'm not going to come in and tell you to start. Just start when you're ready. Yeah, and work at your own pace. Ask questions. It's better to at least try to sort of try the one that we're working on at the time. But if there's something you really need to go back and you feel you need to finish or ask questions about, do that as well. Okay. All right.